Let's graph some polar equations. We're going to start with r equals 2 sine theta. So what that's saying is that the radius is going to be 2 times that. This goes back, or just think of the basic ideas of r equals 5. That would be on a regular coordinate one, 0, 0. Well, r equals 5 is x squared plus y squared equals 25. The radius is 5, and there is no the center is 0, 0, so it's no, the h and k are simple for that. So you would have a circle like that. Well, the sine curve causes you to have some kind of weird other shapes, and that's what we're going to have here. So let's see what happens. Not necessarily a weird shape, just not a normal circle per se. So we are going to identify for each angle, this is the theta here, we're going to take each one of these angles and put it in that place and calculate. So for this first one, r equals 2 sine of the angle 0. Well, at the angle 0, or 360, sine is 0, which means the radius is 0. And that means we're putting a point like right there, right in the center. Then we are looking at the next one, r equals 2 sine pi over 6, which is r equals 2. Well, sine at pi over 6 is 1/2. And the 2's cancel, which means the radius is 1. And so at pi over 6, which is here, we go out 1. Now, actually, let's change something first. I'm going to identify here that 2 spaces is 1, 2 more is 2, that's 3, that's 4, and that's 5. So in between is 0.5s, 0.5, 1.5, 2.5, 3.5, 4.5. You get the idea. What that means for graphing this one is I'm going to go out to here. We need that in order to make this a larger looking figure than it would have been otherwise. Okay, now let's do this with pi over 3. R equals 2 times the sine of pi over 3. And that is for pi over 3, r equals 2 times the square root of 3 over 2, which is the square root of 3. And in the calculator, that's approximately 1.7. So at pi over 3 here, we would go to 1 and 2 and a little bit less than 2. In fact, just a little over, less than halfway from 1.5. So we now have that point. Now pi over 2 will do. R equals 2 sine pi over 2, or 90 degrees. R equals 2. Well, pi over 2 sine is 1. So that means it's the number 2. So we're here at pi over 2. So next, of course, you can see the pattern we're doing here. We're going to do 2 pi over 3, and then we're going to do 5 pi over 6, and then we're going to do pi. Okay, so let's just see what happens now. So at 2 pi over 3, r equals 2 sine of 2 pi over 3, which means that r is equal to, well, sine of 2 pi over 3 is square root of 3 over 2. So we have another square root of 3, or we have another 1.7. And then at pi, 2 sine 5 pi over 6, that's r equals 2. Well, at 5 pi over 6, the sine is 1/2. So the 2's cancel, so we get another 1. And at pi, well, now at this point, I'll give you what they are, because you see how to do this. So let's graph those three. Over 3, we're going the distance of about 1.7. At 5 pi over 6, we're going the distance of 1. And at pi, we're going the distance of 0. So far, we have what looks like it would be a circle. an oval area here, more like a balloon shape, I guess you could say. Okay. Now, if we keep going and we do 7 pi over 6, we're going to have a negative in there. I'm going to give you what these are for these to save us some time. So at 7 pi over 6, it's -1. Well, and I guess I think I will do that. 2 sine of 7 pi over 6, r is equal to 2. Well, at 7 pi over 6, the sine is -1/2. The 2's cancel, and that's how we get a -1. Well, that means we're going to go to 7 pi over 6, but 1 would bring us here, but -1 brings us to here. Well, wait a minute, there's already a point there. That's because 7 pi, negative, well, -1 and 7 pi over 6, which is the way we write this as a polar coordinate, is actually the same as 1 and pi over 6. Because for 7 pi over 6, it's the opposite on the unit circle from pi over 6. So you would, if you went towards 7 pi over 6 instead, but the -1 sent you back the other way, you'd be going towards towards pi over 6. And I'm going to erase a little bit of that. Okay. You'd be going towards pi over 6, 1. And that would be like going to 7 pi over 6, the distance of -1. So they're the same, so you get the same point. And that's what's going to happen with each one of these down here. This one's going to be -1.7. At 3 pi over 2, we're at -2, which was the same as pi over 2, except now going towards pi over 2. Okay, 5 pi over 3, it's -1.7. 11 pi over 6 is -1, and 2 pi is 0. Each one of these repeats the first and second quadrants. So right now, as we move around to here, we get the entire oval, which is then going to look like this. I want to draw straight lines. I want to make it look sort of curved. As we go along here, we end up getting the same things because we're now, with all the negatives, we're going backwards the other direction. So we make the same thing here. So this is our solution for it. We have graphed it. And we've graphed it each time using y equals 2 sine 0 and substituting for the sine, whatever the actual number is, and calculating with it. And you see each one of those. 2 pi over 3, sine of 5 pi over 6. And that's how we get each one of those points, and some that are repeats of them. Now, let's do this with the next one, which is a cosine problem. And before we do the whole page, at the bottom of this one, I have some information about how to do the calculator if you have a TI-84. Many other calculators can do it also. I just don't know their directions, so you'd have to figure that out, of which there are numerous internet support ways of figuring that out, video or written instructions or whatever. So if you have a TI-84 series calculator, you would change two things. You would change to radians, and you would change to polar. So lose two things, change to radian, change to polar. Okay. Then when you go to graphing, you'll see that there's an R there, the y equals thing. You'll see R instead of Y, and the window will show an angle maximum. So then you'll put in the numbers in there based on that, and then take a look and see what it looks like. And you might play with the window as you need to, but this is the basic instructions, a basic way of doing it here. All right. So try it. You don't have to do that polar graphing on the calculator. You can do it with the hand method here, essentially. So now let's look at doing this one. 6 cosine theta. Because it's the number 6, we might go out farther than 5. So this time I will number it as one for each circle. So it'll be 1 and 2 and 3 and 4 and 5, 6, 7, 8, 9, and 10. So let's do r equals 6, and in each case, we're going to do the cosine of theta. So the cosine of 0, the cosine at the angle 0 is 1. So 6 times 1 is 6. Here, r equals 6 times, well, the cosine at pi over 6 is square root of 3 over 2. 2 goes to 6 3 times. 3 times square root of 3 is approximately 5.2. And then r equals 6 times, well, at pi over 3, the cosine is 1/2. So we get the number 3. Here, the cosine at pi over 2 is 0. So 0 times 6 is 0. Let's graph those first here. Okay. So in this case, this graph says 6 and the angle 0 degrees. Here we have a 5.2 and pi over 6, or instead of pi over 6, we could say 30 degrees. Here we see 3, and this time I will use degrees. I'll do 60. I can put 30 degrees here. 60 degrees. This one's 0 and pi over 2, or 90 degrees. So graphing them, the first one is 0 and 6. So I guess I cover up that 6 with it. At pi over 6, because here's pi over 6, and there's 0 and 360. Pi over 3, pi over 2. So at pi over 6, we go out 5.2, so just barely past 5. Of course, that looks like farther, but you can't, by hand, you can't really get better than that. At pi over 3, we're going out 3. At pi over 2, we're at 0. So let's complete and see what happens as we do more of these. At 2 pi over 3, r equals 6. Well, 2 pi over 3, it's negative 1/2, so we get a negative 3. Okay, I'll do 3 of these first before I graph them here. R equals 6 times, well, at 5 pi over 6, it's negative root 3 over 2, which is approximately 5.2. And then r equals 6, well, at pi, it's a negative 1, so we're going out negative 6. All right, so 2 pi over 3 is here. And I would normally head in that direction, except the negative 3 means go the other way 3. So I'm going to here. And then again, for 5 pi over 6, that's here, I'd be going towards it 5.2. 1, 2, 3, 4, 5. I'd be going to about here, except I can't. I have to go the other way. 1, 2, 3, 4, 5.2 is going to be just a little past it. And then pi is this way. So I could go out towards it 6, except that it's a negative 6. So it goes the other way, which, oh, guess what? It's the same as 0 and 6 up at the beginning, same as that one up here. Now, when I do 7 pi over 6, that's r equals 6, negative root 3 over 2, that's approximately negative 5.2. Well, all that does here at 7 pi over 6 is just get us over to this circle here. And each one of these then, as we keep going around, we'll just do one of those others. All right, so I'll give you what those are. You can make sure that you understand how to get each one of these so that you can do it yourself. 5.2 and 6. Okay, now back to here. Look at what we have. You have to try to do light curves between these. Can't draw straight lines. And then I'll go the other way to make a better curve. Okay. Yeah, that's about it here. So that's not quite a circle. It's very close to an oval shaped kind of thing here. And that would be having graphed it. And we did graph it because in each case we put the cosine amount multiplied by 6 so that we got the polar coordinates that we needed. And I could have done that with the others, but you have the idea here. So that's the graph of this particular 6 times the cosine of theta. And you could see it if you set this up right in in the calculator too. Okay. Now let's take a look at what's involved with symmetry. And there's a good explanation of this, page 632 at the bottom of the page. We're going to look at these three things. We're going to test first the polar axis, and then the line x equals pi over 2, and then the origin. So notice our steps, what we'll do. We'll replace the angle with the negative angle. Here, for this one, we replace both of these. That's test 2. And in the origin, we'll replace the radius. So then we change one thing, then the other, then both of them. Or actually, the both of them's in the middle here. That's test 2 for some reason. Okay. And let's pick, or I will give you this particular r equals 1 minus cosine theta. We're going to test to see if it has the symmetry. Now, what these actually mean for the polar axis, it means that we're symmetrical to the x-axis. It means it would flip over the x-axis. It's the exact same on both sides of it. Or it's flipping over the y-axis. Okay? And pi over 2, 90 degrees is like going up in the y-axis. Okay? Or flipping over the origin. Okay, so that's like diagonal flip there. I guess is maybe the best way to put it. What you do is set up the equation by changing the negative. So you change that, you change these two, or you change that one. So let's actually do that. We're going to do test 1. Test 1. Okay, r equals 1 minus cosine theta. We're going to do r equals 1 minus cosine negative theta. And for this one, I'll do it negative theta. And then we're going to calculate here r equals 1 minus cosine. Well, we say cosine theta because there's that rule, cosine of negative theta equals cosine of theta, meaning that the negative for the theta does not change it. If it was sine, that would be a different matter, because then we put the negative out in front of it. We don't do that with cosine because the negative disappears or cancels. So these two are equal. All right, so we're back to here, and what that tells us, because this one and this one are the same, that means it passes this. So it's true, or what are called pass. So it is or can be or might be symmetrical to the x-axis. Okay. Well, I think in this case it means it definitely is. Okay. So yes, it is symmetrical. I can write that word better. Symmetrical to the x-axis. Now we're going to do test 2. Test 2 is the line x equals pi over 2. We're going to replace r and theta with negatives. Okay. So r equals 1 minus cosine theta. So that becomes negative r equals 1 minus cosine of negative theta. Okay. So that means negative r equals 1 minus cosine theta, because the cosine of negative theta is it's this setup where cosine of a negative angle is the cosine of the non-negative angle. So that means we're right back down here to cosine theta, but we have this being negative. So we have to multiply both sides by -1. And I could write that as r equals cosine theta minus 1. But either way, it's different. Okay, the equation is different, so we would call that a fail. This and this are not the same. So what we say is fails, but it means it may or may not have symmetry with respect to the y-axis. There, I've got it. Because the second test was to see if it would flip over the vertical line of x equals 0 on the y-axis. And right now, it doesn't look promising or good at all. Not for that one. So it passes test 1, doesn't pass test 2. Let's take a look at test 3. And I'm going to do this one. Oops. So for test 3, coming back up here, you see it's the origin, and you replace r with the negative. Just r, not the angle. So I would take r equals 1 minus cosine theta, and I would do negative r equals 1 minus cosine theta, and see if we can get back to the original. Well, when I divide both sides by the negative, I get r equals negative 1 plus cosine theta, or cosine theta minus 1. Neither of those are the correct answer for this. So that means it's a fail. So it may or may not. Well, let's make that neater to see, including the so here in the F. So it may or may not be symmetrical to the origin. Sorry, that doesn't write out nearly as well as it should, so I'm going to very quickly write it over again. So it may or may not be symmetrical to the origin. Okay. So what we have here is using this y equals 1 minus cosine theta 3 times, changing something different each time. And in one case, it is symmetrical to the x-axis. In the other cases, it's failed, but it may or may not still be symmetrical. All right, so this is like one of those weird tests. Why do it? Well, there are the cases where it can come into play and be helpful. Okay. Well, let's graph a limithon. Not quite sure the perfect way to pronounce it. I think that actually works. So we actually do the same kind of thing that we did, but we're going to find it gives a different shape. So you will see some of these in the textbook. Go and check it out in section 6.4. And there's some very interesting ones here. There's like 4 or 5 types here. So I'm going to do that. It's r equals 3 plus 6 times whatever cosine theta is each time. And in this first time, it's 1. So we get 6 and 3 is 9. that tells us we have to number this as 1 each because we have to at least go out to 9. 6, 7, 8, 9, and 10. Okay, pi over 6, I'm going to do the same thing. R equals 3 plus 6 times, well, cosine theta, if theta is pi over 6, we have square root of 3 over 2. So that gives us approximately 8.2. And then R equals 3 plus 6 pi over 3. Oh, wait a minute, I meant to actually put the thing. Pi over 3 is 1/2. So 2 goes into 6 3 times. 3 plus 3 is 6. And R equals 3 plus 6. Well, at pi over 2, the cosine is 0. So it's 0 plus 3, so it's 3. Okay, well, let's graph those first. 0 and 9 are out here, so cover up most of the number. And of course, here's pi over 6, pi over 3, and pi. And here is, oh, not pi, pi over 2, and this one's pi. And down here is 3 pi over 2. And of course, over here is 2 pi, or 0. So if I keep going, I'm going to get these numbers. Okay, there's a negative 1/2 here, and it cancels out the 6, and so that makes it 0 and 3. And at pi over 6, 5 pi over 6, we get a negative 2.2. Yep, at pi, we get a negative 3. 7 pi over 6, it's a negative 2.2, and then 0 and 3 for these. 6 and 8.2, and 9. So I'm giving you those since you see how to do them at first with the ones that I've written out. So I think I'm going to make this a real 0, looking 0 there. Okay. Now let's actually put these. So there'll be 9 at the angle 0. And so that's starting towards 9 places towards or from 0 here. Well, okay, and we get to this one. Pi over 6 is 8.2 out there, which is about here. At pi over 3, we're at 6, so that's this one. At pi over 2, we're at 3. That's here. Okay, so we've got what looks like half of the or something like that. And then at 2 pi over 3, it's 0. Now, 5 pi, let's see, pi over 3, this one's 5 pi over 6. 5 pi over 6 towards this one, but going the other way because it's negative 2.2. Okay. And then at pi, we're going to 3, negative 3, which normally we'd be going 3 this way, but because it's negative, we're going to go to here. And then at 7 pi over 6, we're going out to negative 2.2, which means going the other way from 7 pi over 6. So, and then 7 pi over 6, so 4 pi over 3 is 0. So what we actually have here is, let me do this curve. And you notice what it's doing now is it's actually curving around like this. Well, let's see what happens with the rest of the numbers. So at 4 pi over 3, let's see, or is it 7 pi over 6? 4 pi over 3 here. So 4 pi over 3 is back to 0. So we've got a 2 pi over 3 and 4 pi over 3, which aren't even across from each other as zeros. At 3 pi over 2, we go, it's a positive. So we go to 3 pi over 2 and we go 3 places here. Okay. And then at 5 pi over 3, we're going to 6. So this is 5 pi over 3. And we're coming up here to 6. And we have 8.2 and 9. 11 pi over 6 is 8.2. And then we have 90 for this one. So we're going to now continue this. And now let's use this yellow marker to show where it goes around. And then on the inside circle, and it comes out of the inside circle, but keeps on going. That's an interesting little thing. And that's what the mason, oh, to check my vocabulary for that, how to pronounce it. In fact, actually, I think I'll do that with some online help because every year I practice pronouncing it, and every year I'm not certain I remember. So let's see if it will pronounce it for me. Now I can't find the right definition thing. This is usually something that does it. In this case, oh, I should put definition. Hold on a moment, and I will be able to say it right, I think. Pronunciation. Good use of the internet if I can get this to work sound-wise. Hold on, just had it. Okay. Limacon. So it's not doing it with the little C sound, so I think it should be different from that a bit. Anyway, as far as math goes, we now see how to graph it. There are other versions of this too, and that's actually what the next couple of pages show. There's a rose curve, and there's a lemniscate. Those are easy to pronounce. Well, let's actually look at doing them. This one is a rose curve. So we're going from this one that has this like dimple on the inside, and then there's this one where we're going to see that it's going to give us a rose, and or sort of, it's going to give us petals. So here's how we'll graph it. And I'm going to do r equals 5, and then we're going to put the sine of 2 theta. Oh, well, first, actually, this one takes a little more like figuring out, so let's actually figure it out. R equals 5 sine, well, 2 times theta, it will be 0. So R equals 5, so 2 times 0 is 0. And the sine at theta, or the sine at 0 is 0. So we still get a 0 here. Well, when we do R equals 5 sine of pi over 6, we have to do it by 2, so it's 2 pi over 6, which makes it pi over 3. R equals 5 pi over 3, the sine is square root of 3 over 2. So basically, instead of 30 degrees, the 2 here makes it 60 degrees, or pi over 3. So we can call it 30 and 60 degrees too, just to make it easier for you. And then if we do 5 times square root of 3 over 2, we get approximately 4.3. Actually, let's graph the first one. We have 0, 0 here. And then for this, we're going to go out by 5s for it. So I'm going to do 1, so that's 0.5, 1, 0.5, 2, 0.5, 3, 0.54, 0.55. And then here I have pi over 6, and here's pi over 3, and pi over 2, and 2 pi over 3. So let's do 5 pi over 6, and then pi. So we'll start with those. So this one is 4.3 and pi over 6. Even though this double angle made it 60 degrees or pi over 3 for the calculation, it's still at pi over 6. So we go pi over 6 for the direction, and we go 4.3, which would be about here on the graph. Okay. So we have 2 points so far. And then pi over 3, if we calculate that, okay, we're actually going to get now, let's see, R equals 5 sine of 2 pi over 3. And at 2 pi over 3, again, it's square root of 3 over 2. So we're actually going to get the exact same answer. 4 pi over 3. Okay, so I will write it out so you can see it, square root of 3 over 2. And then with pi over 2, okay, r equals 5, the sine of, well, pi over 2, 2 times the pi over 2, the 2's cancel. So it's sine of pi, which is r equals 5. Well, at pi, the sine is 0. Oh, so we're back to a 0 here. So let's graph this one here, and then graph this one here. So we have an interesting shape. This is where I have to tell you, we don't have one here. I don't have pi over 4 on here, but it's maybe an appropriate thing to actually do 5 pi over 4, because it looks like that maybe there should be a point here, because this is coming up like this, and it should go up to another number, and it's going to come down like this, like a pedal does. So let's figure out separately, since it's not on the graph there, we'll do it for pi over 4. So r is equal to 5 times the sine of 2 pi over 4. R equals 5, the sine of 2 pi over 4, which is pi over 2. R equals 5. And at pi over 2, or 90 degrees, the sine is 1. So that's equal to 5. So we get the angle of a radius of 5 and the angle of pi over 4, r and theta. So let's actually put that up here. At pi over 4, we're going to go all the way to the 5 here, which means that this is going to that last part, too much of a straight line. There, so we have a pedal. And that's the first part of our answer. We have a correct pedal here. Well, as we continue going, and you can see the correct way to do it, but so you can do any of these by hand. I'm going to put the numbers down here so we can graph them, and you can see what they are. Negative 4.3, negative 0.3, and 0. Ooh, so let's graph those first. So at 2 pi over 3, we go the other way, negative 4.3. So we go to here. And then at 5 pi over 6, we go the same thing. And then at pi, we go 0. So if we were to do the in-between here, because that's 5 pi over 6, this one here in between would be 3 pi over 4, and we would end up going a negative 5, so we go here. And again, you could do that one by hand there. Not supposed to make an exact point like that. It's supposed to be just, a curve at the top. I think that's a little bit better of a leaf. Ooh, for somebody who can't draw, I'm doing pretty good today. So that's the leaf part here. And you see where it's actually the second quadrant angles, but because of the negatives, we end up in the fourth quadrant. Well, now for the third quadrant ones, we're going to actually get the inside the third quadrant because we have positive numbers here. And for the fourth quadrant angles, we'll be forced with the negatives to go back into the second quadrant. So now let's graph the rest of these. First, I'll put these angles of 7 pi over 6, and then 2 pi over 3, 3 pi over 4 pi over 3 here, and 5 pi over 3 here, and this is 3 pi over 2, and 11 pi over 6. And the in-betweens are the 45s. So we'll still use those in between for here and in between for here. So we're going to get 4.3 here and 4.3 here. So we'll get the same curve. Now I'm not drawing it as well either. And then 4.3 and 4.3 there. And I'll yellow those in, and you can see why it's called a rose curve. Now, roses do look a little different. This is a little simplistic, but it makes for a nice name for it. So whoever dreamed up the name, hey, it makes sense. It helps us remember that's what it's going to look like in some form. If this number was different, then that would change that. And this number could be different too and make it all different sizes for it. Okay, so that's a rose curve. Now let's do it again with a lemniscate. And a lemniscate is going to be, this one's different as an R squared. So we figure out what R is, taking calculating here. We put in, actually, this is a good one to do this with R. So we'd have to do plus or minus. So actually what we would do is take the square root. R equals plus or minus the square root of 25 cosine 2 theta, which is equal to plus or minus 5 cosine of 2 theta. So if you put 0 in for the cosine of 0 in here for the angle, and then twice that is 0, the cosine of 0 is cosine of 0 is 1. So we get the square root of 1. Actually, where do I work it out here? So actually, let's do, how do I say where to do the plus or the minus? Okay. Well, actually, we can do it with the plus or minus because they're just going to go opposite ways here. So I'll use the pluses right now. R equals 5 cosine. 2 times 0 is 0, and R equals 5 cosine of 0 is 1. So square root of 1 is 1 times 5, we get a 5. And square root of 6, when we put it in here, when we do that, we're going to get 3.5. So you're going to put pi over 6. Oh, but 2 pi, because we're going to have to multiply it by 2. 2 pi over 6 would make it pi over 3. And a pi over 3, it's 1/2. So I'll do that as R equals 5 cosine of 2 pi over 6. And that makes it a 3. And R equals 5 1/2. So you put that in the calculator, take the square root of 1/2 times 5, and you get approximately 3.5. Well, pi over 3, you're going to get a negative inside the square root, and that's because we won't actually graph it. So this one, it's like not used. And you'll see why in a moment when we graph the thing. Actually, that I'll run through it. Pi over 2, when you do the calculations, you'll get a 0. So I'm going to give you the numbers here, and then we're going to graph some of these. At 2 pi over 3, that one becomes not used. 5 pi over 6 gives you a return of 3.5. Pi gives you a return of -5. Notice it's these two, but with negatives. 7 pi over 6 is negative 3.5. That'll not meter. 3.5. 4 pi over 3 is not used. Not used. Okay, I'll write that one better. 3 pi over 2 is 0. 5 pi over 3 is not used. 11 pi over 6 is a 3.5, and 2 pi is 5. And now I'm going to graph those on here. And we're going to go again, we're going to graph at 1/2 for each line. So it'll be 1. So skipping 1 each time, 1, 2, 3, 4, and 5. So at 0 and 5, we're here. At pi over 6, is here pi over 6. Here's pi over 3. I'll do these first because it'll make more sense. 2 pi over 3, 5 pi over 6, and pi. 7 pi over 6, 4 pi over 3, 3 pi over 2, 5 pi over 3, 11 pi over 6. That covers all of those here. So at pi over 6, we're at about 3.5. That's here. Well, the reason why we don't use pi over 3 is because what we have here is this. When we do 11 pi over 6, we have 3 pi over 5. or 3.5. I'm sorry to say that wrong. And so what we get is this. And when we do the other ones with the negatives and the positives for each of them, we actually get the same type of thing over here. So I'm going to graph those to show you what they look like. So this one's here. So what you actually see is at pi over 3, there is nothing along the line anywhere. And the same with 2 pi over 3 and 5 pi over 3, which is why those are not used. 4 of them are not used because they're not used. They're nowhere part of the graph. The 0 one that's here is used with pi over 2 and 3 pi over 2. So those are the zeros. And that covers getting to 0 for each of these two like leaves on here. And so these are mirror images of each other, which is why the negatives and positives can handle it. If you put this in the graph as plus 5 root cosine 2 theta, you would get 1/2 of this. The positive one would give you this one. And then you do a second on your y equals, it would be r equals, because you graph this with a polar coordinate. The negative one would give you this side. So if you only put in the square root, if you only put in the positive one, you would get half of it. You'd have to put the negative also to get the other half, and you see both of these on your graphing calculator or any kind of graphing utility. So there's another interesting one with some of the lines not being used as opposed to being negatives going the other way and just doubling up, which is what we see in the other types of problems. So let's review quickly the things in here, because there's a lot in this section. Graphing a basic polar equation means just figuring out the trigonometric answer for each of the sines or cosines as we get them. Plugging it in, doing the number, getting the radius. And then you have the radius and an angle and plot a polar coordinate. And if you do that for all of them, you get this type of look for a sine, a polar equation with sine. Notice it's sort of going up on this 0 and then going like an up arrow down. And for cosines, they go left to right. In a way, I guess you could say. But they're done the same way, where you put in the correct amount for the cosine of whichever angle. And remember that you can graph on the graphing calculators using the method that's shown here. You can check for symmetry by doing these 3 tests, test 1, 2, and 3. And you'll want to remember that all they are is simply switching or first making the angle negative, next making both the angle and radius negative, and then making the radius negative. And that's based on whether it's the polar axis or the x-axis or the y-axis or the origin. And then we're graphing a limousin, I think it is, because when I tried on the internet, it didn't do the right C. It's a French word with the sounds that those who know French would be able to distinguish that. I believe it's a limousin, something like that. So it looks like this with a little bubble inside it. And that's because of the negatives going backwards from some of the lines. And then a rose curve. So it's one of them 4 times, essentially. And then a lemniscate. It's a mirror image of them, a plus or minus with a square root. And you have now seen a number of things involving graphing with polar coordinates. And hopefully that helps. Thank you for watching and listening.